So we'd like to find a way to measure gravitational acceleration g very accurately. And I said we can measure time differences very accurately by a laser timer. And we can actually measure distance between two objects very accurately by a number of methods. So what I would like to find out is if I just use two laser timers, can I measure g by reading the time difference in the first, the time difference in the second laser, and the distance between them. All right? Now, how do I do this? Well, first, let's put our axes onto this problem. All right? So let's say this is the y-axis. Okay. I don't even need to plot another axis here. Y is a function of t. Now, I don't know what the ground level is. I can choose any ground level here. Apparently, at the end, it should not matter. And I don't know what the velocity of this object is. But to be able to continue with my solution, I actually need to define these quantities. So what I will define is that I'll say the first laser is at some height h from the initial point where motion starts, or from my ground point. And obviously, the second laser will be at h plus L. I'll also give an initial velocity v0. I'll define these symbols, but be very careful. These symbols cannot appear in my final solution. Okay? Hopefully, by the time I actually get to the end of the problem, these symbols have dropped out from my equations. All right? Now, what is y of t? Well, let me be very simple. I'm starting with velocity v0 at time t equals to 0. So it will be v0t minus 1/2 g t squared. All right? Any comments, any questions? This is motion with constant acceleration. So if I know y of t, how can I actually calculate delta t1 and delta t2? What defines delta t1? There will be two times that this object crosses my lasers, right? And delta t1 and delta t2 are the differences between these two times. So I can actually define, let's say, th1, th2 as the times my object crosses the first laser or second laser, and or let me call these t up and t down. This is t down 1, t down 2, and t up 1 and t up 2. So delta t1 will be t up 2 minus t up 1. Delta t2 will be t down 2 minus t down 1. How can I calculate t down 1 and t down 2? What's the equation that defines these two times? Well, they are the times for which my object crosses the lower laser. So what is my height when I actually cross this laser? It's exactly h. So y at t downs must be h. v0t minus 1/2 g t squared is h. Let me write these down in a different way. I'll say g over 2 t squared minus v0t plus h is equal to 0. This is a quadratic equation. How do I solve quadratic equations? All of you should know how to solve quadratic equations. So what is t down 1 and 2? Or let me remind you, what is if I have ax squared plus bx plus c is equal to 0? I have two solutions. What are those two solutions? Minus b over 2a plus minus 1 over 2a square root of b squared minus 4ac. How many of you are familiar with this formula? How many of you have never seen it? Excellent. Resting easy. I was panicking for a while. But this is just solving quadratic equations. I have a quadratic equation here. So I'll just solve it. I have minus b over 2a. So I have v0 over 2 times g over 2. The first term. Plus minus 1 over 2a is 2g over 2 square root v0 square, right, b square minus 4ac minus 4g over 2 times h. So it's going to be v0 over g plus minus 1 over g v0 square minus 2gh. This is t down 1 and 2, two solutions. So can you tell me what is delta t2? That is the lower time. Delta t2 is td2 minus td1. So what is that? td2 is the largest one. v0 over g plus square root of 1 over g square root of v0 square minus 2gh minus v0 over g minus 1 over g square root of v0 square minus 2gh. Okay? So v0 over g is cancels. I have 2 over g square root of v0 square minus 2gh. That's going to be my delta t2. How about delta t1? If I do this calculation for delta t1. Your friend is right. I don't actually have to go through all this calculation again. The only thing that actually changes for delta t1, instead of h, I have h plus l. So in this calculation, delta t1 should be 2 over g square root of v0 square minus 2g h plus l. Is the logic here clear? That's the nice thing about using algebraic formulas. I'm not putting in any numbers so that I can actually understand what the general case looks like. All right? So here, I'm just replacing h by h plus l. Okay. Now, what were given to me in the problem? I was given L, I was given delta T2 and delta T1, and I would like to solve for G. What else is appearing in my equations? V0 square and H. So somehow I need to get rid of these two unwanted quantities. So let's see. I'm going to write this a little bit differently. I'll take the square of both sides. Delta T2 square. It will be G square over 4 equals V0 square minus 2GH. And similarly here, G square over 4 delta T1 square would be V0 square minus 2G H plus L. And here's the magic. If I actually subtract these two equations, I will get rid of both V0 square and H. So let's subtract them. G square over 4 delta T2 square minus delta T1 square is equal to V0 squares cancel to each other, 2GH's cancel each other, I have 2GL. So at the end of the day, this is pretty nice. What I get is I can cancel one factor of G here. G apparently is 8L divided by delta T2 squared minus delta T1 squared. Did I reach my goal? And that was the critical point here. I needed to express G in terms of delta T1, delta T2, and L, and that's exactly what I have. Now, if I have very good measurements of L, delta T1 and delta T2, I'll have a very good measurement of G through my experiment. So I reached my goal. How about the units? What's the unit of L? Meters. What's the unit of delta T? Any one of them? Seconds. So this whole formula tells me it's meter per second square, which is the unit for acceleration, G. So unit-wise we are okay. The limits are really hard to think about in this problem, okay? But one thing we can easily say is if L is too large, right, G must be very, very large so that you actually cross both these trajectories. Or if I actually make L small and then delta T1, delta T2 small, I will again have that's a tricky limit, maybe too early at this stage. But the only limit I can think of is L going to 0, G going to 0. That actually makes sense. Question?
I think it's not true.
Why?
L and delta T's are bond each other. They have a bond.
They have a?
Bond.
Okay, but I treated them as independent variables to solve for G. You must always think of what are your independent variables and what are your variables which are not independent. Here, our solution shows that if you have delta T1 and delta T2 and L, you can get G out of this.
When I say you can't make L 0 without make delta T.
You are right. You can make. Okay, so this is a tricky limit. What I was talking about. When L goes to 0, delta T2 goes to delta T1. So G becomes indeterminate in the limit sense. And in that sense, then you have to use the L'Hopital rule to calculate this limit, something you're going to learn in Math 101, hopefully. And you will actually see that G works in that case too. Okay? Any other questions? No? All right. So, this one-dimensional motion gets a little bit boring after a while, right? Especially motion with constant acceleration. This question is pretty much the most tricky case I can think of, okay? If I can relate G to 2, delta to 1, and delta to 2. There was actually another reason why I solved this question. Here's a practical question for you. There are so-called atomic clocks, which are very accurate. And the scientists actually used an atomic clock to measure G to 10 significant figures. I'm making up numbers here, all right? But 10 significant figures. No, of course, I'm just making it up. And G also changes, right? It's different in the equator and at the poles. It's actually different between Ankara and even Istanbul, okay? Now, why would a scientist want to measure G with such big accuracy? And he was very well funded for this experiment. A lot of people have given him a lot of money. What kind of companies would you say want to know G very precisely? Not really, no. Everyone is thinking about flying. I want you to think in the other direction. What does G tell us? What do you think happens to G if there is a big cave underneath us? Or if there's an iron ore which is very, very dense? What was the real reason for G? It's gravitational acceleration, right? So if you're actually near a cave, G is slightly less. If you're at a point where there is a lot of liquid under Earth, G is a little bit less because liquids are not as dense as rocks. So it's usually oil companies or geophysics companies which would like to measure the value of G at this precision, because at this precision it actually tells us a little bit about what's going on under the soil. All right? So actually, funny thing, the guy who actually did this measurement, I don't know if he's rich or not, he got a Nobel Prize for a different reason. And then he was the energy secretary, the Enerji Bakanı of United States for a while. So measuring G is fun business. I mean, really, if you read the paper, he tells that if there is a big truck parked outside their lab, the value of G changes. They can actually detect the presence of a truck. Okay. So, any questions? No. But I think this one-dimensional motion is boring. Okay. Really. We have looked at especially for constant acceleration, that's as complicated. Our quiz question and this problem is as complicated as it can get. Now, thankfully, we are not living in a one-dimensional universe. It's fun to speculate about what would happen if I lived in a one-dimensional universe. But we are living in a universe with 3 space dimensions at least. That's we know of, right? So how do we look at motion in higher dimensions? First thing we need to do is we need a way to mathematically represent our central quantities like position, velocity, and acceleration, not in 1D now, but in 3 dimensions. So to do this mathematics, we need something. We need a way to represent all quantities not as just numbers. Our velocity, our acceleration so far has been just a number. Now we must represent all our quantities as vectors. Okay. Now, what's a vector? Well, what's the standard definition of a vector? Something that actually has a length and a direction. Okay, so there is a vector has what we call magnitude, which actually means its length, and a direction. And whenever I have these mathematical objects vectors, I'll put a small arrow sign onto the letters to denote vectors. All right? Now, it turns out when you, there are a lot of physicists in this course, that's why I'm saying this. When you actually go to classical mechanics next year, or maybe in the 3rd year if you take mathematical courses, you'll define a vector in a different way. You'll say it's a mathematical object which transforms according to certain rules under rotation. So there's a better mathematical definition of a vector. This is the amateur definition if you want, but that's going to be enough for Physics 101. Anything that has a direction and a magnitude. So now once you define any mathematical object, you must define some operations on it. So first thing I will do is vectors can be multiplied by numbers. So for example, 5 times, or if I have a vector A, three times A is also a vector. The only thing that changes is the magnitude. It's actually 3 of these added onto each other. How about minus 2A? When I have a minus sign, the direction of the vector changes. So it's going to be, this is going to be another vector. And here's a bit of nomenclature. Now we all want to impress our grandmothers. Okay, and if you go today to your home and if your grandmother asks you what you did, you can say, well, we learned about vectors and numbers. She'll probably say, hey, you've been studying numbers since elementary school. So we want to impress her. We're not going to call numbers numbers anymore. We're going to call them scalars. Okay? So scalar means something which is a number. Okay? It doesn't change under rotation. That will be the more mathematical definition. But when you hear scalar, you'll think about a number. When you hear a vector, you'll think about an arrow. That's all I want to say. And just in a few weeks, we'll say more grandiose statements like kinetic energy is a scalar while momentum is a vector. Okay. In the end, we're not saying something terribly complicated. All right? Good. So vectors can be multiplied by scalars. That's great. Now, vectors can be added is our next rule. So what do I actually have? If I have two vectors, A and B, A plus B will be another vector. I'll just join these vectors so that the tip of one vector becomes the starting point of the next vector. Let's call this C. So I can give you a geometrical definition of what sum means. When I say vectors can be added and they can be multiplied by scalars, I immediately also mean that vectors can be subtracted from each other because I can multiply one vector by minus 1 and add it to the next one. All right? What else can we do with vectors? We'll see that the length, sorry, let's go back to the other color. The length of a vector is called norm or magnitude. And it's represented, so this is A. A magnitude is represented by putting A in absolute value sign, inside absolute value sign. This is just a number. So if it's equal to L, it means that from the starting point to the tip, the arrow thus has a length of L. Now, all these geometric definitions are nice, but you will never see a professional physicist or a chemist we can go to anyone's room in our offices. No one is actually drawing arrows, right? And think of it as an engineer. You're trying to design the next, I don't know, cellular phone. Do you think people in Apple's offices are actually drawing, vectors to add vectors? Does that mean they do not use vectors? No. We need a way to take these geometric definitions and turn them into algebraic definitions, which means we can actually turn these into numbers so that we can feed them to computers, or we can do our calculations using algebra, right? And in that case, what do we need? We need components of a vector. All right. Now, if I want to turn everything into numbers, I need some sort of reference frame, right? So I'll actually do this in 2 dimensions now. What I can say is, let's say this is my vector A. How can I represent this vector? Instead of telling you an abstract quantity with an arrow on it, I can much better tell you how to get to the tip. I'll say if I move AX units in the X direction and AY units in the Y direction, I will actually reach to the top of my vector. So in many cases, instead of thinking of A as an abstract object, in 2D, I will actually think of it as something that's made up of 2 real numbers. What would be the norm? What would be the magnitude of my vector? Because this is a right triangle, it's going to be square root of ax squared plus ay squared. Now, this is not only it. I actually want to be able to express, I would like to invent a new kind of notation. First, let me make a definition. I'll talk about unit vectors. It's not something to be scared about. Unit vector has only one definition. They are vectors with magnitude 1. So their length is 1. And whenever I have a vector with unit magnitude, instead of putting an arrow on it, I will put a hat. Okay? Unit vectors are shown with a hat on them. All right? Now, here's what I'll do. So the unit vector's magnitude I know, but its direction can be anything. So unit vectors are generally used to specify directions. Okay? And it turns out there are special names given to units in the x direction, y direction, and z direction. Okay? For the x and y directions, the unit vector along x is called I hat, and the unit vector along y is called j hat. So instead of thinking about a as made up of 2 numbers, that's one notation. Instead, I can write a is going ax unit in the x direction plus going ay unit in the y direction. All right? So in a moment, you'll see why this notation is better when I actually start defining vector multiplication. All right? Now, in 3D, it's going to be even more. I need one more unit vector. So the unit vector along x is called I hat. The unit vector along y is called j hat. And the unit vector along z is called k hat. How do I actually reach any point? I need three components, ax, ay, and az. So any vector A can be written in terms of these three components. Okay? Now, how about the magnitude of a vector in 3 dimensions? It's just going to be, I need to use the Pythagoras theorem 2 times. So it's going to be ax squared plus ay squared plus az squared all square root. Now, adding vectors, adding a plus b. Geometrically, it required some work. I need to carry one vector to the tip of the other. But when I express things algebraically, it's actually going to be very simple. Why? A is ax I hat plus ay j hat plus az k hat plus b is bx I hat plus by j hat plus bz k hat. And when I add these up, it's going to be ax and bx are both multiplying I, so I can actually factor them together. I can collect them together. It's going to be ax plus bx I hat, ay plus by j hat, and az plus bz k hat. Similarly, if I actually multiply a vector by a number, I'm just multiplying all of the components of that vector. All right. Now, adding my vectors or subtracting them or multiplying them by a scalar is easy. Now I need to be able to multiply vectors. Okay. A word of caution, your book does not do vector multiplication until later. But I think this is the right time to talk about vector multiplication. Okay? So this is going to be a little bit different from your book. But we'll save time later. Now, vector multiplication. It turns out there are 2 kinds of vector multiplication. The first is an operation when I take A and B, and out of 2 vectors, I'm not making another vector, I'm making just a number, a scalar. Okay? And this is shown by a dot between them. So this is just going to give me a number or just a scalar. So this is called the scalar product, or because there's a dot there, called dot product. Let me first give you the geometric definition. If I have 2 vectors, A and B, which make an angle theta, the geometric definition of A dot B is the magnitude of A times the magnitude of B times cosine of the angle between them. All right? So if I have 2 vectors of fixed length, when is the dot product maximum? When is cosine theta maximum? When theta is 0. So when they are aligned, A and B are aligned in the same direction, dot product will be maximum. When will the dot product of 2 vectors be 0? The dot product of these 2 vectors will be 0 when they are at right angle to each other. Okay? And when will it be minimum? Or when will this be negative? When does cosine become negative? After 90 degrees between, if the angle is between 90 and 180 degrees, then cosine theta will be negative. So vectors, the dot product between two vectors being negative means they are pointing in mostly opposite directions. And really, think about the following. If I take a projection of B onto A, what is the length of this projection? It's going to be B magnitude cosine theta. Now if I multiply this projection by A, it gives me the dot product. So this is telling me something about projection of B onto A. So this tells me how aligned my two vectors are. Right? Now, how do I define the same dot product in terms of the components? In terms of components, how will I be able to define the dot product? And here is the nice thing. I don't really have to think much about it. Remember, one more thing. What is A dot A? Let's be careful. A dot A. What's the angle between the same vector? A dot A means A magnitude cosine 0, right? Cosine 0 is 1, so this is A magnitude square. So the length of a vector is square root of the dot product of it with itself. All right? Now let's go to components. I have, let's be careful, x, y, and z. And along each direction, I have I hat, j hat, and k hat. First question. What is the dot product of I hat with itself? We have just said this must be I hat absolute value squared. I hat magnitude squared. What was the length of vectors with a hat on them? 1. That was our definition. That's a unit vector. So this must be 1. The same thing applies to any unit vector. How about I hat dot j hat?
0.
What was my definition? It must be magnitude of I hat, magnitude of j hat. What's the angle between I hat and j hat? What's cosine of 90 degrees? Cosine of, I'll call it pi over 2. That's 0, right? So when two vectors are perpendicular to each other, their dot product is 0. So I hat dot j hat is 0. Similarly, I hat dot k hat is 0. J hat dot k hat is 0. Why do I think of these unit vectors? Because without any problem, now I can actually multiply two vectors. A dot B is going to be ax I hat plus ay j hat plus az k hat dot product with bx I hat plus by j hat plus bz k hat. What? Well, there are 9 terms here. So let me write. The first term is ax times bx I hat dot I hat. The second term will be ax times by I hat dot j hat. But that term will be 0. I hat dot j hat is 0. Similarly, I had something I hat dot k hat here. It's going to be 0 again. The only terms which actually survive is ax bx, ay by, and az bz, right? So I'll have ay by j hat dot j hat plus az bz times k hat dot k hat. But we have just said all of these are 1. So as a result, I can easily say a dot b is multiplication of the components. All right? You see that I didn't have to do another definition. That's the nice thing about unit vectors. If I can do something with unit vectors, I can do it for all vectors. All right? That's the nice thing about component notation. Now, in the remaining time, I'll actually define one more vector multiplication. Okay. So the second way to multiply vectors is you take 2 vectors, a and b, and out of them we make another vector. So all of these are vectors. Because this is creating one vector out of these 2 vectors, sometimes it's called the vector product, or because it's shown by a cross instead of a dot, this is more commonly referred as a cross product. And it turns out it's a little bit more involved to define this thing geometrically. Okay. So, first of all, this only works in 3 dimensions. Okay. You can generalize it to other dimensions, but it's not going to be exactly like a cross product. There is something called an outer product. But the way I'll define it works only in 3D. So if I have 2 vectors, A and B, with an angle theta between them. If C is A cross B, it obeys the following rules. First of all, magnitude of C is C magnitude is A magnitude times B magnitude times sine theta. And you may say, hey, great, this is just like the dot product. Instead of cosine, I have sine, so it should be simple. But now we have to define a vector. So I told you the magnitude of the vector. Now I need to tell you the direction of the vector. Here is the rule. C is perpendicular to both A and B. This is somewhat interesting. How can I be perpendicular to both A and B? If I'm perpendicular to B, I'm certainly not perpendicular to A. And if I'm perpendicular to A, I'm certainly not perpendicular to B. This works only in 3 dimensions. That's what I said. So now the only way you can actually be perpendicular to both A and B is you must go out of the plane. So you're either coming out from the screen or maybe you're going into the screen. So my definition is still not fixed. I'm perpendicular to both A and B, but I need one more rule. C direction is determined by the right hand rule. And that is something I actually need to show you. How do I calculate A cross B's direction? I know that it's either going to be coming out of the screen or going into the screen. So here's how I do it. Please stop taking notes and follow me. Now, I'm taking my right hand, first of all. Be careful, it's your right hand, not your left. Okay. You take your right hand. You have your 4 fingers. Point them along the first vector. So this is A cross B. I'm pointing them along the first vector. I can still orient my palm in any way. I'm doing my orientation so that my palm faces the second vector. Okay. I'm closing my hand towards the second vector, and my thumb tells me the direction of C. So C, apparently in this case, is going into the screen. It's not coming out of the screen. Let me do it again. This is like a magic show. I like doing this. So I have A. I can orient my palm. I orient it so that I'm facing the second vector. I close my hand towards the second vector. My thumb tells me the direction of C. All right? So apparently C is into the screen, and I'm going to show it by the symbol, a cross with a circle around it. That means into the screen. So very quickly, let me define D as B cross A. B cross A. How would I do B cross A? Let's be careful. Now I'm actually pointing my 4 fingers not along A, but along B. I still can orient my palm. I orient it so that I am facing the second vector. And I'm closing my hand along the second vector to first. From the first vector to the second. My thumb tells me it's coming out of the screen. So D would be coming out of the screen. Which tells me that A cross B is not equal to B cross A. So this cross product is different from our multiplications. When we multiplied numbers, 3 times 5, or I should say scalars now. Let's impress our grandmother. 3 times 5 is 15. 5 times 3 is 15. But A cross B for vectors is not equal to B cross A. Actually, A cross B is minus B cross A. And that actually tells me, I'll need to tell you one more thing. What's the geometric meaning? I said A dot B tells me how aligned my vectors are. What does A cross B tell me in the geometric sense? Let's remember A, B, and theta. A cross B as a vector magnitude was A magnitude B magnitude times sine theta. Now, if I take a perpendicular line to the tip of A, what would be the length here? It will be A magnitude times sine theta. So what would be the area of the parallelogram here? A magnitude, B magnitude times sine theta. So it's the area spanned by A and B. Okay. Actually, we will see that this cross product defines an area vector. You'll see that in 102. So the areas can also be defined by vectors. Cross product is used to define area as a vector. Right. I need to write down one final thing. I'm running out of time, and I'll actually not really prove this, but how about for unit vectors I, j, and k? What is the cross product of any vector with itself?
0.
The cross product tells me the area, right? So when I close the vectors, there is no area left. This is 0. Same thing for j cross j and k cross k. But here is the interesting thing. What is I cross j? I'm taking my 4 fingers, pointing them along I. I can still rotate my thumb and palm. I'm rotating it so that it faces j. When I close, what I get is k. So I cross j gives me vector k. Similarly, j cross k gives me I. K cross I gives me j. So let's write these down. I cross j gives me k. J cross k gives me I. And finally, k cross I gives me j. And using these relations, you can actually find, I'm not going to prove it here, but if I have A cross B, in terms of components, I can actually calculate them by writing down I hat, J hat, K hat with AX, BX, nope, AX, AY, AZ, BX, BY, BZ, and calculating the determinant, maybe of this. I'm just doing this to scare you. AY, BZ minus BY, AZ minus J hat, AX, BZ minus AZ, BX plus K hat, AX, BY minus BX, AY. All right? Now, I will review the part about cross product on Thursday, and there will be a quiz about vectors in our next lecture. See you in 2 days' time, in 3 days' time.